Hello, this is Dr. Song-Shu of Keysight Technology. In this short video, I will demonstrate to you the setup of MAC imaging in liquid. The MAC imaging in liquid setup is very much identical to imaging liquid of contact mode and AAC mode in liquid. MAC sample plate, position the sample in the middle. Add liquid cell. Push down and rotate the two doping lock. Then on back side, we need to connect the MAC signal cable, which is a 3-pin plug. Now we can add liquid to the sample plate. Make sure the liquid fill up the entire bottom of the liquid cell. Now the sample is ready to be mounted on the AFM. Next, to check, make sure that the laser is still aligned and detector is still aligned. Sometimes you have to realign the detector because the added liquid could shift the refractive laser spot, so you can adjust the detector. Once that's done, open the imaging mode, make sure it is on AC AFM. In the tuning window, want to switch the drive mechanism on AC AFM from AEC to either top MAC or MAC. When his choice is on the MAC mode imaging is going to be driven by the MAC sample plate. When we choose the top MAC, the MAC signal will be driven from the solenoid in the nose cone. Now let's try to adjust to the MAC, so we drive the MAC imaging using the sample plate. Here, the menu tune, we choose from 2 kHz to 50 kHz and click menu tune. Let's narrow down this tuning from 2 kHz to 28 kHz. Again, remember, in liquid imaging, you cannot use automatic tune. You have to use manual tune. Here we identify a peak around 14 kHz. We will adjust the driving frequency on the peak of this resonant frequency of this cantilever. Now we are ready to approach. Click the approach, and the approach starts. Here notice that we put IP gain of 11 and 20. The set point cannot be adjusted during approach. Motor speed somewhere around 10, and stop at value is 80%. Setting time is 30 microseconds. Now the approach in progress window disappeared, and we know that the approach stopped and tip and sample is engaged. Here, let's switch the tag to servo. And set point is stopped at 1.6 volt. To increase the force, you could decrease your set point a little bit to ensure that tip and sample engage firmly. Here on the image window, we choose have 4 pages. The first is topography, second is amplitude, third is phase, and last one is topography, but we choose the retrace. Now we are ready for imaging. In order to see the image more clearly, we could click on the first image, which is topography, and click this button, which will make this image appear to be larger. Let's start image. Here the scan speed, we choose 1.7 Hz, and scan size is 2.5 micrometers. In order to optimize the image, you could look at the image and then adjust the I gain and P gain. Let's see what happened when I reduce the I gain. When you reduce the I gain from 11% to 2%, we notice that the topography image started to appear to be blurry. The integral gain, which is I gain, basically adjusts how sensitive the scanner respond to the up and down topography of the sample. So in order to have a high sensitivity, to have a crispy image, you need to have a high gain. However, what happens if your gain is too high? Let's change gain from 2% to 11%, and then let's further increase from 11% to 20%. Now notice the image appeared to have a certain vibration noise. If we look at this oscilloscope window, we also notice this vibration noise right here. And this is caused by the integral gain appear to be too high, and therefore the sensitivity is too high, and it causes the feedback loop to oscillate itself. So we go back to the servo control and start to reduce the I gain. At the same time, look at image and look at oscilloscope. As we notice, when the gain is reduced back to 11%, the image appears to be clean and noise is gone. To ensure extra stability, we could reduce the gain another 10%, go down to 10%. Now, once we are sure about our parameters, we could click this button and restart image, so we can capture the entire image in high quality.